The previous video focused mainly on using a calorimeter to determine the specific heat capacity of a metal. With that, we used the equation MCAT equals MCAT, and the objective was to calculate that specific heat capacity of the metal or the solid object. And we can compare that with tables of reference data to try and figure out what the object is actually made of. Well, that's not the only thing that we can put into a calorimeter. Into a calorimeter, we could also put a chemical reaction because chemical reactions also absorb or release heat energy. And if I allow that heat energy to flow into water, we can actually measure the amount of heat that either flows into or out of the water and calculate its associated energy of that reaction. And that's actually pretty important, pretty valuable, because just like specific heat capacity is to an object, an enthalpy of reaction, or delta H, is to a chemical reaction. So chemical reactions do not have specific heat capacities. That only belongs to single objects, not reacting. What chemical reactions do have is something called a delta H value. When a delta H means that every chemical reaction is going to give off a certain amount of heat per mole of a limiting reactant. So we would need to make two measurements, an amount of heat and amount of moles of that chemical reaction. Delta H is officially called a molar enthalpy. And what it specifically means is it's the amount of heat that's given off per mole of reaction. Now that's not something that we've seen before, mole of reaction. I'll explain what that is in a little bit. The units of delta H are a lot like C, but instead of being in terms of grams, this one's in terms of moles. So this is the number of joules per mole reaction. Delta H's come in two flavors. Reactions can either be endothermic or exothermic, and you've probably heard of these terms before. Endothermic means that heat is entering the chemical reaction. Heat is flowing in. Exothermic means that heat is leaving the chemical reaction and that heat is flowing out. So what I'd like to show you now is something that you should have seen before in a biology class. It's something called a potential energy diagram. And what we do is we allow this diagram to run over a period of time, usually during the length of that chemical equation. And you can see how energy changes as a function of time. Here's an example, and this is for an endothermic chemical reaction. You can see on the y-axis that we have plotted energy. Now this is potential energy. And if you remember from way back in the beginning of the year, potential energy is the energy that's stored in bonds. Kinetic energy is like thermal energy. It's like the temperature of a substance. But potential energy is stored in the bonds. Now on the x-axis, they have something called the reaction pathway. And that's okay, but you could also substitute that with time. So this is how the energy of the reaction changes over time. You should see two plateaus. These two plateaus essentially represent the beginning and the end of our chemical equation. The first plateau should belong to the reactants. This is how much potential energy the reactants have. The second plateau belongs to the products. This is how much potential energy the products have. And in between, you see this weird hump. That's what happens to the energy of the system as you move from reactant to product. That hump represents the chemical reaction itself. Every single chemical reaction is going to have this classic hump in between. The distance between these two plateaus, between the reactants and the products, represents the difference in energy between the reactants and the products. And this is what represents delta H. The distance from the reactants to the top of the hump, however, represents something called activation energy. This is the amount of energy that it takes to start a chemical reaction. And the way that we start most chemical reactions is by taking every single bond that belongs to the reactants and breaking them. That can take a heck of a lot more energy. Because what will end up happening then is we have to reform bonds and store some of that energy back in before we can actually make our products. So delta H tends to be a lot different than your activation energy. We call this the activation energy barrier. It's almost like the first hill that you have to climb on a roller coaster. You're storing up a whole bunch of energy as you click and clack your way up to the top of that hill before they release you into the rest of the roller coaster. One last place that you should really understand on this graph is the top of the hill. I marked it with an asterisk. This is the point at which all bonds are actually broken. And that is an extremely unstable state for atoms to be in. We know from, again, previous chapters that atoms bond to gain stability. So if they're all unbonded, that means it's extremely unstable and extremely temporary for those particular atoms. But it's a state that they have to go through to go from reactants to products. Notice in this picture here, delta H is kind of in an upward way. So to go from reactants to products, you have to go up. That means that the products have more energy than the reactants. So energy is being stored. This would represent an endothermic reaction. So if you're actually climbing from the reactants up to the products, that should represent an endothermic reaction. So let's take a look at what this looks like for an exothermic reaction. Here's your graph, and notice what's changed here. The reactants start up high, and the products end up down low. But we can still mark the same places on our graph. So the distance between the reactants and the products is still known as delta H. This is how much energy has been exchanged during the course of the chemical reaction. And again, in this case, notice that you have to climb down from the reactants to get to the products. This means that the products have less energy than the reactants did, that the reaction had to give out heat. This is pretty classic for an exothermic chemical reaction. However, in order to get there, you still had to climb the first hill of the roller coaster. That is marked by this distance here. That's your activation energy. And you still have a top of the hill. That is that temporary weird state where all bonds are broken. And they want to try and get out of that as quickly as possible to get back to some stability down at the end. A couple of little things that you probably should be aware of. Signage. We know that signs in math are really, really, really important. And that's going to be true here when we start to talk about delta H a little bit more in conjunction with chemical equations. So when delta H is positive, that means that we've added heat into the reaction. That's usually true of endothermic equations. So when delta H is positive, your reaction is endothermic. When delta H is negative, that means that heat has left the chemical equation. And that is usually indicative of an exothermic reaction. So delta H positive, endothermic, delta H negative, exothermic. This is usually something that you're going to have to add in after you're done with the calculations for this particular type of problem. Another thing, how do these feel to the outside observer? Exothermic reactions are usually giving out heat, so heat is flowing out. Exothermic reactions tend to feel extremely hot because the heat will flow out of the reaction and into something like your hand that's going to be sensing it. Whereas endothermic reactions tend to feel really cold because the heat will be flowing out from the surroundings and into the chemical equation or into the chemical reaction. I want you to actually see what this looks like in real life. How do scientists actually use this information and write it down? Here are two examples. These are called thermochemical equations. Again, that's thermochemical equations because it's not only chemicals, but it's also the the heat part of this whole thing. It's like a giant recipe for how you actually make this thing happen. Let's take a look at the top equation. You have C6H12O6 plus oxygen. That sounds like cellular respiration to me. In other words, we're burning sugar. Notice the sign on delta H. Delta H is negative. This is an exothermic process. Energy is being released. And that makes sense. Your body or plants store sugar so that you can use it later to release energy back into the system, negative delta H. How about the bottom equation? CO2 plus H2O makes sugar and oxygen. That's photosynthesis. And notice the sign on delta H, it's positive. In this case, it would be like a plant going through photosynthesis to try and store energy in the form of sugar. That's an endothermic process. We store the energy so that we can use it later on. So I hope these two examples are helpful in trying to understand why delta H is important. Again, this is like a fingerprint for a chemical equation, for a chemical reaction. Endothermic is usually positive, exothermic is usually negative. After you calculate a delta H value, it's typical to report them in this fashion, right next to a chemical equation, turning it into a thermochemical equation.